Welcome to Middle School Mathematics Module 1 for Praxis Prep, specifically covering arithmetic and pre-algebra. This is sponsored by TLC Tutoring Co. and Arkansas State University. To begin with, we start with numbers and number parts. On the Praxis, the only types of numbers will be real numbers. Real numbers can be categorized into one of two groups, rational or irrational. So here's the different groups that make up rational numbers. You have the natural numbers, 1, 2, 3, 4, also called the counting numbers. You also have just whole numbers. Those are all the natural numbers and also 0. That's considered a whole number. And then you have integers, sometimes called our friends, because it's the ones you always think of. So it's the natural numbers, including 0 now with whole numbers, and their negatives. That's your three main types. And then additionally, we have fractions. Fractions are the numbers between the integers. Like, for instance, 1/3 is 0.333, a repeating decimal that we can see, or something like -1/4, which is -0.25. That's a decimal with an ending. Next, we have what we call irrational numbers. So when they're expressed in decimal form, they have no repeating pattern and they never end. The most common example of this is the irrational number pi. So pi, when you learn from circles and geometry, is 3.14159, etc., 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 and it goes on forever and it never ends. Also, radicals and non-perfect squares, like the square root of 2, the square root of 3, or square root of 12, these don't have endings. They go on forever. And even though the square root of 12 could be simplified to 2 times the square root of 3, it doesn't simplify to an integer in the same way that the square root of 16 is 4. So if a number that is in a fractional form has an irrational number, then that number is also irrational. Now, as we're talking about mathematics operations, the order of operations, and mathematical properties. So addition is the process of combining values. The first thing we really learned in mathematics, right? And the process of taking away is called subtractions. We call these inverse operations, that they undo each other. Now, multiplication is the process of repeated addition of a set value. Division is the process of separating numbers into groups with a set value. Multiplication and division are also inverses. And you can see here 4 times 5 is 20. That's 4 plus 4 plus 4 plus 4 plus 4. Or 20 divided by 5 is also 4. You see how they undo each other. In the same way, when we're looking at these problems, you're going to have word problems, right? We're going to have various words that allude. They suggest the operation that it tells you what to do. So it might not tell you directly, but they might give you an implication. So the word like sum implies that addition is necessary. So this is a typical list of words that you might very well see on typical problems. Minus and difference for subtraction, product, double for multiplication, quotient, groups of for division, and etc., etc. Now, when we talk about order of operations, when we start doing mathematical work, we have to do them in the correct order. Now, the way this is normally done is we have parentheses, exponents, multiplication, division, addition, subtraction. Now, that is using the acronym, the mnemonic PEMDAS. Also, some people use please excuse my dear Aunt Sally. That is a classic. So if we didn't have a convention, we would get different answers to the same problem. So let's take this one for existence. You can see this right up here. Now, if we didn't have a set order, we'd all get different answers, but we're going to follow the steps. So PEMDAS, we're going to start with P. We're going to do the parentheses. So 2 times 4 is 8. You can see it moves to the right. Now we need to do the exponents. You see that square there. We should use that. 8 squared is 64. So now we have 64. There's no multiplication, but there is division. 64 divided by 2 is 32. Now all that's left is addition. 4 plus 32 is 36. So that is the classic application of PEMDAS. Now, we have some specific properties that we use a lot when we're doing these different things. So the commutative, associative, and distributive properties, they all make sure that we solve the math problems the correct way and all get the same answer. So we have to know these properties so that we can apply them. So the first is the commutative property. It tells us we can swap the order of two numbers that are added or multiplied, and the answer remains the same. For example, 6 plus 3 is 9, and 3 plus 6 is also 9. 3 times 9 is 27, and 9 times 3 is 27 as well. Now, notice this is addition and multiplication, not subtraction and division. The commutative property does not work for that. A second one is the associative property. So, when you start putting the parentheses around these kind of problems, if we associate in the order that we do, if we're, again, addition and multiplication, a plus b plus c, it doesn't matter if I add a and b first or b and c first, I'm still going to get the same answer. Same idea with a times b times c or a times b times c, however you want to do it. This is the same game with 2 plus 4 plus 6, 2 times 4 times 6. You're going to get the same answer no matter the order you do it. Again, only for addition and multiplication, not division and subtraction. Finally, the distributive property tells us that when two numbers are inside parentheses and added together, and then they are multiplied by the number outside the parentheses, you can distribute those numbers to those inside the parentheses. So that sounds really crazy, but all this means is if you have something in parentheses and something outside, you can multiply the outside times the inside. So 5 times 2 plus 3 is the same as 5 times 2 plus 5 times 3. That's 10 plus 15 is equal to 25. So that you would get the same answer either way. Now, here's a quick problem. You'll have many of these in these to help you keep your skills fresh as you're working. So, which of these following are equal to 10? So take a moment and take a look. Okay, so let's move on and let's see what we have. Now the first one is 51 thirds is the same as 17. 17 minus 7 is 10. B, you can see, actually gives you 16. C is 2 squared times 3. That's 4 times 3, or 12 minus 2. That one's 10. D, 3 plus 1 squared minus 7. We have to do parentheses. 4 squared. 16 minus 7, 9 plus 1 is 10. The bottom one is a similar issue. You have a lot of 10s in there, but it ends up with 25 minus 20, so it's 5. These are just to help you get comfortable with remembering your PEMDAS orders. Next, we want to talk about exponent rules and radicals roots. So, much like multiplication is repeated addition, exponentiation, which is a great word, is repeated multiplication. It represents exponentiation with superscripts, those little numbers above. So in general, a to the b power is a multiplied by itself b times. So like 2 to the third power is 2 times 2 times 2, which is 8. So there's a few very cool rules that we want to remember because these are very useful when you start messing with exponents. So first of all, if you have a real number and it has a power, you just multiply the real number by itself. 2 times 2 times 2. Now, look at this next one. Rules for adding or subtracting exponents. Now, if you have x squared and x squared, you have 3x squared and 2x squared. You don't know what x is, but x squared will be the same everywhere. So if you have 3 of them and you have 2 more, you can put them together and have 5x squared. Now let's take those same ones and let's multiply them rather than add them. Here, we need to take the coefficients in front, and we're just going to multiply that like normal. 3 times 2 is 6. But with the powers, x squared times x cubed, we're going to add those powers, and it's going to be 6x to the 5th. So since we added when we multiplied, we're going to subtract when we divide. So in this example, 8 divided by 2 is 4. Those are regular coefficients. X to the 8th divided by x to the 3rd is x to the 8th minus 3, or 4 times x to the 5th. As we continue our exponent rules, if we raise an exponent to an exponent, so that's powers of powers, you're not going to add the powers, you're going to multiply them. So in this case, 2 is going to be raised to the 4th power, that's 16, and x squared to the 4th power is 4x squared, or x to the 8th. Now, if you have seen negative exponents, say x to the negative 1, well, we don't like negative exponents. We want to get rid of those. What we do is we flip them. So if you have something to a negative exponent in the numerator, you're going to flip it to the denominator. If it's in the denominator, you're going to flip it to the numerator. Anything you've got to do to make it positive so you can use it. Now, anything to the power of 0 is 1. This is a common problem where they'll give you a big hairy number raised to the 0 power, and it's just 1. In the same way, any number to the power of 1 means something times itself once, which means you didn't actually do anything. So it's just mean no repetition, and that's the same as just the number itself. Another thought is 1 raised to a power, because 1 times 1 times 1 times 1 is just 1. Doesn't matter how many times you do it, it's still 1. So like 1 to the 26th power is still 1. So you just keep going. Now, the rules for exponents apply to binomials. Be careful with this one. So we're saying x plus 1 squared. The binomial has two terms. Remember, that means x plus 1 times x plus 1. This is not the same as x squared and 1 squared. That's not the same thing. This would be the FOIL process, which we'll get into a little bit. So this ends up being x squared plus 2x plus 1. So keep that in mind. Now, we talked about exponents. Roots are the inverse operation. Remember, we're all about how do we undo things. So we say a square root means to find the number that you multiply by itself to get the number under the radical. For example, the square root of 64 is what number times itself gives you 64. In this case, it's 8. 8 times 8 is 64. A cube root, if you can just imagine, right, is it multiplies by itself 3 times to get the number under the radical. So the third root of 64 would be 4. 4 times 4 is 16. 16 times 4 is 64. Now there's also two ways to write roots. You can use that root symbol, right, that radical symbol, or you can say x to the 1/2. The 1/2, so powers that are fractional are the same as roots. So you can see radical notation is just another way of writing these fractional exponents. So if you have an exponent inside of a radical, that exponent becomes the numerator of a fractional exponent. So take a look at this. 8 to the 2/3 power is the same as 8 squared cubed, which is the same as the third root of 64, which is 4. Now, finally, we have what we call roots and radicals imperfect squares. Now, we talked about imperfect squares means that you get an irrational number, right? So a perfect square is when you take a square root and you get a nice integer, a round number, a whole number. So like the square root of 4 is 2. But that's not always the case. The square root of 5 is 2.2361, and it just keeps on going. That's an imperfect square. Well, the trouble is we need to find ways to simplify these because we don't want to have square roots of huge numbers. We want to simplify them down so that we can look at them easier. So consider the square root of 80. Well, that's not a perfect square because the square root of 81 would be 9. So it's close to 9, but not exactly, right? So what we can do is we're going to start pulling out the perfect squares from 80. So let's say we pull a 5 out. That would be 16 times 5. 16 times 5 is 80. You can split those radicals. The square root of 16 is a perfect square. That's 4. So the square root of 80 is the same as the 4 times the square root of 5. Now, again, like exponents, there's a few specific rules we need to follow involving roots. So if you're adding or subtracting imperfect squares, you're going to combine like terms because square root of 3 may be an irrational number, but as long as you keep using the square root of 3, it's consistent. So if I have 2 square root of 3's and 3 square root of 3's, I put them together, now I have 5 square root of 3's. You also can multiply and divide with imperfect squares. But if we're going to multiply, what we're going to do is you multiply the coefficients. So 2 times 3 is 6. And you also are going to multiply the radicands. That's the numbers underneath the radical sign. So in this case, that would be the square root of 3 times the square root of 3 is the square root of 9, which is a perfect square, which is 3. Then 6 times 3 is 18. That helps us simplify these down so that we can utilize them. So here's a little example. If we want to simplify this exponent and roots, now looking at this, what could we do? We have x squareds and we have x cubes. Take a moment. So as you probably saw, here, you can combine the x squareds. I have 1x squared and 4x squareds, that's 5x squareds. The 8x to the third, I can't really do anything with that, so I'm just going to put it in front so it's nice and neat. Here's another practice. If I have something raised to a power, right, I have 4x squared y cubed z4 to the second power. I'm going to use my rules. And that's going to be 4 squared 16, x squared squared, that's 2 times 2 is 4, y cubed squared, that's y to the 6, and z to the 4th squared, z to the 8th. In the same way here, we can do the same thing with roots. If I have 5 square root of 3 and negative 8 square root of 3, I can put those together. That's going to be negative 3 times the square root of 3, and then minus 2 square root of 2. I can combine and simplify. Scientific notation is a way of writing really big, very large, or very small numbers easily. It's no fun writing 0, 0, 0, 0, 0, 0, 0. It's very confusing, and it's very likely that you'll make a mistake if you're typing something in. So let's talk about what you're going to do is take a large number and write it in scientific notation. So this is the number 700,000. It's a lot of zeros. So here's what you're going to do. You're going to move the decimal behind the first non-zero digit, in this case 7. So you're going to make sure you got a 7, then the decimal point. And you're going to count how many places you moved that decimal. Since it was 700,000.0, right, you moved the decimal 5 places. Now you're going to represent 700,000 with a power of 10. Every space you move is like multiplying by 10. So I did it 5 times. 7.0 times 10 to the 5th is the same as 700,000. Now let's try a really small number, which is also important. So whatever this is, 0.000000008 in scientific form. So same idea. We're going to move the decimal so there's one non-zero digit in front of the decimal, an 8 in this case. So that's 8.0. We count how many decimals we moved. That was our original number. We moved the decimal 9 places, 8 zeros, and then the number 8. That's going to be our exponent. But because it's a tiny number, you're dividing by 10 every time. So this is 8.0 times 10 to the negative 9th. So remember, negative powers for really small numbers, positive powers for really big numbers. Now let's talk about fractions. Now, we've talked about whole numbers primarily, but when we're talking about fractions, there's a couple of specific parts in here. So some fractions or parts will have an integer, a whole number, right, and a fraction. That's called a mixed number. So like 2 and 1/4. Then you also have fractions where the numerator is greater than its denominator, and they're referred to as improper fractions. So for example, 9/4, which is the same number as 2 and 1/4, just written as an improper fraction. So to convert numbers, you want to multiply the integer part by the denominator and add that to the numerator. So you can see it here, 2 and 1/4, 2 times 4, that's the denominator, is 8. We're going to add 8 to 9 because we have 8 more parts. So now we have 9/4. Now, if we want to multiply two fractions together, what we're going to do is we're going to multiply straight across. You're going to multiply the numerators and multiply the denominators. So in this case, 2/3 times 3/4, it's going to be 2 times 3, which is 6, and 3 times 4, which is 12. Now we're not going to simplify, but that's how we would do it. Now if we're going to divide, we're going to flip. We're going to keep the first number the same. We're going to flip the second fraction, and we're going to multiply them. So this becomes 2/3 times 4/3. 2 times 4 is 8, 3 times 3 is 9, and you get 8/9. Now, if we want to add or subtract, there's a few extra steps, right? So we have to make the denominators the same. We need a common denominator. Well, we can see here I have 1/3 and 2/5. Well, those are not common. I got to find a way to get a common denominator. So the least common multiple of 3 and 5 would be 15. Neither fraction has 15, so we're going to have to change them. We're going to scale them up. Since 3 times 5 is 15, we multiply 1/3 by 5/5, and you get a denominator of 15. Similarly, 5 times 3 is 15. You're going to multiply 2/5 by 3/3. As you can see here, we didn't change the number. 5 over 5 is just 1. 3 over 3 is 1. We just scaled them up to make it an easier number. And I'm going to end up with 5/15 and 6/15. Now, since the denominators are common, we just add the numerators. 5 plus 6 is 11, 11/15. Now, decimals are numbers that place a value that show amounts less than 1. So, like 18.5 is the number halfway between 18 and 19. It's just a different option than doing fractions. Now, most of us think about currency. This is the easiest way to think about the conversion of decimals to fractions. So, think about how 4 quarters make $1 and 2 quarters make 50 cents. 1 divided by 4 is 25 cents. 2 fourths would be 0.5, 3 fourths 0.75, 4 fourths is 1. That's a simple way to see how they are related to each other. Now, percents are an amount out of 100. It's similar to a fraction in that instead of just some number of pieces, it's 100 pieces. So if you have 85 pieces out of 100, you have 85%. So if we said you made 85% of the test, that doesn't mean that you answered 85 questions or that there were 100 questions. It could have been 10 questions or it could have been 5,000 questions. We don't know. But it does mean if there were 100 questions, you would have gotten 85 right. So to convert from a decimal to a percentage, we multiply the decimal by 100, and we're going to move the decimal place 2 places to the right. So 1 quarter is the same as 0.25 multiplied by 100. That's 25%, and you can see how that holds the same all the way across. Now, percent change is we have algebra strategies when we're dealing with percentages. So when one value is unknown, we use this formula. So percent change is the final number minus the initial number divided by the initial number times 100. This is formula when you're talking about a value change from a certain percent. So let's say you have a $30 shirt is on sale for $15. You say it is 50% off, right? We've all liked to get a good deal. $30 is the initial value, 15 is the final. So, and 50% is the percent change, but if you only knew 2 of the 3 values, percent change, final, and initial, you could use this formula to find the missing piece. So, let's say a shirt is on sale for $50 after a 20% markdown. What if we want to know what did it initially sell for? Well, you could plug 50 in as our final value and negative 20 as the percent change. Note, the value went down, so it's negative, right? If this was a mark up, you would be a positive number. So 20% equals 50 minus initial over initial times 100. When you rearrange that, that's going to be $62.50. That's the initial price. So here's a little practice. You can try this with some scratch paper or whatever you've got handy. A shoe store has 50 pairs of tennis shoes in stock. If 30% of the store's shoes are tennis shoes, how many total pairs of shoes does the store have to the nearest whole number? So using our formula, we're saying I have 30%. That's 50 pairs minus the initial number over initial times 100. So the initial, once I rearrange, is 50 divided by 0.3, or 167.67 shoes. Now, I can't have 0.67 shoes, so we roll down, right? I can't have 2/3 of a shoe floating around, so we're just going to say I have 167 shoes. A box of cereal costs $2.58 with tax. If the sticker price, the price on the label is $2.30, what percentage are you paying in tax? This one would be the same thing. You're going to use the same deal. You're going to say 258 is the final minus 230 divided by 230 times 100. That's a 12.2% increase. So let's talk about ratios. Ratios are simply a comparison between two numbers. There's 3 ways you can write a ratio. You can write a ratio using the word to, you can use a colon, or you can write it as a fraction. So let's say you have a bag containing 3 blue balls and 2 white balls. We write out the ratio of blue balls to white balls. You could write this as 3:2, 3:2, 3:2, or 3/2. They all mean the same thing. Now, you know, when two parts of the ratio are stated, there is an implied total that could be found by adding them together. For example, the ratio of white balls to the total number of balls would be 2 to 5. Didn't say there were 5 balls, but we can infer this, right? And a proportion just means you have two ratios that are equal to each other. That means if you simplified all the ratios down, you would get the same number. So let's talk about Susie baking a cake. So the recipe she has calls for 2 eggs for each cup of flour. Well, she sees she has 4 cups of flour and she'd like to use it all. How many eggs does she need? So this is a proportion. Recall, a proportion is just a statement that two ratios are equal. So our two ratios are eggs in recipe over flour in recipe is equal to Susie's eggs over Susie's flour. Notice the eggs are both on top and the flour is both on bottom. We plug in our known values and we see that 2 to 1 is equal to x to 4. And then from here, you're just going to do your normal algebra process. You need to isolate that variable. So x is being divided by 4, so you're going to multiply both sides by 4. So that's 2 over 1 times 4, and that's 8. So she needs 8 eggs. Now, one of the most common applications for ratios and proportions is using them to compare two things that are the same shape but different sizes. So think about a scale model of a building. You have the shape of the building and it's the same shape as the real building, but it's shrunk down, right? This is usually called a scale factor if you're talking geometric figures. So if you double all the sides on a shape, you can see the scale factor is 2. You double everything. So you could write that relationship as using the ratio of 2 to 1. So here you have a parallelogram that's 10 feet by 18 feet. If it's a 2 to 1 ratio, the smaller one would be 5 feet by 9 feet. You just divide everything by 2. So let's talk about the ratio of boys to girls in Mr. Bennett's class is 2 to 5. How many girls will be in the class when there are 12 boys in his class? So we set up our proportions. We know the class is 2 to 5, here written as fractions, and we know that there are 12 boys in the class over the unknown number of girls. Now we're going to cross multiply. 5 times 12 is equal to 2 times girls. That is the same as 60 is equal to 2 girls. We divide by 2 and we have 30 girls when there are 12 boys. So the value of B is directly proportional to the value of C. When B is 10 and C is 15, what is B when C is 20? So directly proportional means that when B goes up, C goes up. So as we said, being directly proportional means it would be B over C. If B increases, C also has to increase. So we know that it's 10 to 15, and we need to find B over 20. 15 times B is equal to 10 times 20. 15 times B is equal to 200. B is 13.33. Now, factoring multiples and prime numbers. It's important that we keep these straight in our eyes about what we're talking about. So multiples is when you take a number and you multiply by some integer. So multiples always go up. So like the multiples of 6 are 6 times 1 is 6, 6 times 2 is 12, 18, 24, 30. You keep multiplying and you keep going up. So when we say the least common multiple, the LCM of two numbers, is the smallest number that is a multiple of both numbers. So let's try this with 3 and 4. So first we could say, let's list the multiples of 3. 3, 6, 9, 12, 15, etc. You can see you're running all the way up. And then we do the same thing with 4. Now, we can see there are multiples that they have in common. 12, 24, 36. But those are the common multiples, but we want the least common multiple. So the least common multiple would be 12. Prime factorization is taking something and factoring it down to primes. Now, recall that factors are numbers that we multiply together to get a product. So prime numbers, as we probably recall, are numbers that are only divisible by 1 and themselves. So here's a list of the first 10, right? 1, 2, 3, 5, 7, 11, 13, 17, 23, 29, etc., right? And, maybe with a few extra. But all positive integers can be written as a product of prime numbers. So you can write 15 as 3 times 5. 18 can be written as 3 times 3 times 2. And so what you can do is you can take any number and break it down to its prime factors. So take 18. If you split it to 2 and 9, and then split 9 to 3 and 3, those are all primes, so you're done. So you could write 18 as 2 times 3 times 3. And if you multiplied it out, you get the same answer. It's just another way to present a number. So let's try this. What's the prime factorization of 125? For this, you can't use 2 and you can't use 3. You divide 125 by 5, you get 25. You divide that by 5 and you get 5 again. So 5 times 5 times 5 is the prime factorization of 125. Now, something to talk about is the reasonableness of results, which is a lot of R's. But when you're doing mathematical operations, we sometimes need to stop and think, is this reasonable? Does the solution you have calculated make sense in context? Is it a reasonable answer? So let's talk about John's coupon entitled him to 1 free ticket for every 3 tickets he purchased. If he purchased 17 tickets, how many free ones did he get? Now the problem implies division. 1 free ticket for every 3 tickets. So simple division would suggest you get 5 free tickets. But however, if we misread this and we said we multiplied 3 by 17, we would see, oh, he got 51 free tickets. Is that reasonable? No, that's way out, right? So use your understanding of logic to catch computation or setup errors that give you an unreasonable solution. This also could be if you mistype something in your calculator. Just because it came out of your calculator doesn't mean it's the right answer, right? And that completes Middle School Mathematics Module 1. Congratulations! So we're going to be moving on to Module 2, which will cover algebra. Thank you very much.